Yeah, so today we are going to discuss about this thing, generative AI. If you have to tell one word that you know about generative AI, can you guys unmute yourself and just tell me what that would be? Any volunteers?
ChatGPT.
Awesome. And anybody else think any other word?
LLMs.
Okay.
Tab 9.
Tab 9. Okay, I do not know what this is. Yeah, primarily like the whole world got to know about this generative AI through ChatGPT. Today we'll be discussing a bit about what is so special about this ChatGPT kind of models. We'll be looking at OpenAI team behind ChatGPT and how they actually started this work and how they got it to this state. Sometimes discussing history will help us use this tool a lot more better. So then we'll be looking at some of the basic challenges. So anybody tell me what are the basic challenges that you faced using ChatGPT?
You have exhausted the daily usage.
Okay, daily usage.
Yeah, it will not give the up-to-date data.
Yeah, that's another good one. Okay, cool. I think two are good enough for us to get started. So primarily, if you look at the evolution of ChatGPT, so there is GPT-1, GPT-2, GPT-3, and GPT-4, like different kind of models evolved over time. And if you observe amount of parameters that are involved here, so it moved all the way from millions to billions, billions to trillions. So you don't need to know what the parameters means. We'll come to that in a while. So, but just remember, like there are these numbers going high and high. The reason for them is they are being trained with a lot more data. So all you see in this training data column, it's everything on the top plus the bottom one. So for example, GPT-2 is trained with Common Crawl, Book Corpus plus Web Text, and GPT-3 is all the above plus this. So basically, the entire training data that is used to train these models have been growing. And for GPT-4, we do not know what that training data set is, but we see like it's much, much larger than all the other GPT evolutions. Therefore, it required this trillion parameters to hold all that information. So basically, as more data is available on the internet, models have been utilizing all of those data in order to make them better and better over time. So let's talk a bit about their evolution. So at the very heart of it, for the language model, it's all about generating the next word. So given a set of previous words, so the task is to just generate what is the next word. An example could be the cat sat on a, and what is the next word? Any guesses? What that could be?
Matt.
Awesome. So it could be Matt. It is mostly because it rhymes well, and most of the cats sit on the mat, not on the dining table or so. I mean, they do, but most of the time they be on the mat, and that's the data that is available on the internet as well, right? So therefore, these models favor this mat more than anything. Primarily, this can be expressed in a simple language like probability of output given some input. Technically, this input is nothing but the previous set of words. And mathematically, this can be expressed as a probability of the next word UI given all the previous words like I minus k, 2, so on, I minus 1, right? So you can imagine all of these are previous words given conditioned on this thing called parameters. And this theta is something called parameters. We'll understand more detail about it. Given a model with these parameters and given this input, what is my next output? That's the model objective. This has been the core model objective across all the GPT versions. And this kind of probability of output given input is like GPT-1 kind of generation models, which were doing this. GPT-2. Initially, GPT-1 was mostly looking at use cases like story generations or mimicking a conversation given a training on some conversation. It was all creative tasks. And then when we moved to GPT-2, they were trained as something called multitask learners. Here, primarily, the model objective has been changed a bit. Still, we want to generate probability of output, but given not just input, but also a task. Like, for example, a task could be translate to French. This could be the task. Let's say we give the English word perfume. Here we are giving the task and this is our input. Given this, we want to get an output. So in this case, we are conditioning it to generate a French translation for perfume. So in this case, again, it is going to generate the next possible output conditioned on these context. So this is what we call it as context, or in simple terms, previous words. And as you can imagine, these previous words have this k length. This k length is what we call it as context length, which is limited. So like if you see here, there are models which will offer 1k context length, 2k, 16k, 128k. So there is a limited information that you can pass to LLM in a single call. And that limited window or number of words have been growing with the model evolution. So basically in this GPT-2, we are giving this task, translate to French, and we are giving a word, English word. And we expect this result to be translated into French. And probably it'll output something called parfum. This is a French translation for perfume. This was GPT-2. So then there were like GPT-3. These were like few short learners. Still, probability of output is what we want to generate. But now it is conditioned on input, the task, as well as some examples about task. For example, if I say the task is classify the sentiment, let's say this is a task, and we give some examples like I love the product. So obviously the sentiment associated with this will be positive, and this is the example that we are giving. So like this, we can give few more examples to it, which is what we are calling it as few short examples or few short learners. So the idea is the LLMs should learn to deal with this task a little more better by looking at this few short examples. Given a task, given these examples, and then we giving the output. Let's say this phone has an amazing battery. It needs to still predict the next word as output, but the next word output or next set of words outputs is conditioned on this context. Remember, this again needs to fall within that k length. In this case, the output that it probably generate is positive. GPT-4 and GPT-4o, instead of giving input, task, and examples, they were also giving reasoning. Like these examples were not just input and output. They were also saying, okay, here is the input, and here is the thought process, and here is the expected output. That's how they train it. And then they will give, okay, given this input, you do your thought process, and then you generate me the output. We understood now the context window. What does the context window mean? And we also understood what does the output mean. And in this context window, we also understood what is a task, what is a few short examples, etc. Now, the next unknown is what is this parameters? All these GPT models. So G stands for generative. Why it is generative? Because it is predicting the next word. And this T stands for transformer. In order to understand these parameters a bit more, we need to understand what these transformers mean. At the heart of it, transformers are nothing but neural networks. These neural networks come in very different flavors. There is a BERT before GPTs. This was like encoder, decoder, transformer. We don't have to get into the details of what encoder means, what decoder means, and all of that. You can imagine, like, if it is a translation task, encoder understands what the English thing and logic is, and decoder will then start to decrypt word by word and produce the next translation. So you can just imagine at that high level understanding that should be sufficient. GPT models are kind of decoder only models, right? They don't have this encoder piece in that. But why it is decoder only? Why? What is the disadvantage of not having encoder? All of that, probably, if you are interested, we can cover in next upcoming sessions. But for now, this knowledge is sufficient, right? So at the heart of it, all of this BERT, GPT, encoder, decoder, everything is a neural network, right? So therefore, it is important to understand what a neural network looks like. We take this same example of the cat sat on the, this is the input. It should fall within this context length. So we give this input, and there will be something called tokenization layer, which kind of converts all of these words into numbers. And it also maintains this map. Given a word, what is the numerical representation of it? And this is nothing but tokenization. It splits these incoming words and generates some numeric values to it. Those numbers are actually passed to something called input layer. You can imagine all this x1, x2, x3, all of these are numerical representations for all of these textual words. These numbers are kind of passed to something called hidden layers through these edges. And each edge will have some number associated with that, which we call it as weights. Each of this input will be a weighted sum against the weights. For example, here, the x1 is multiplied with 0.15 in order to calculate this a1. Like, one of the component is that x1 and the other component is x2. Like that, all the components that are connected to it will be like weighted sum against this, and the activation will be calculated. So once this activation is calculated, there is something called activation function, which will be taken and will produce this a1, a2. You can imagine these are again numbers. In the next layer, again these numbers will be multiplied to calculate T1, T2, T3. And this final layer is called output layer. The number of green nodes here will be equal to the number of unique tokens we have seen in the training data set. Because these are next word predictors, given this set of words, it is going to predict the probability for all of the words that are possibly possible in the training set. In this case, as you can see here, the model says the cat sat on the, and it is predicting floor as the next possible output. So the training data set will involve a lot of such kind of information, like the cat sitting on the mat. So obviously this neural network is kind of predicting some wrong next word, which is where it will try to compare with the ground truth. So the ground truth says the cat sat on the mat, not floor. So obviously there is a error. So in this case, it should start increasing the probability for mat and decrease the probability for floor. That kind of understanding and the error correction, it will do by technique called gradient descent. Sorry, is there a question?
Yeah, you mentioned ground truth. What is ground truth?
Yeah, so the ground truth is nothing but the training data set that we use for this model. What we do is we will have a data set like the cat sat on the mat. So when we are training this model, what we do is we take this as input and we kind of mask the next word. We don't show that to LLM. Basically, we are asking it to predict what could be this masked word. When it predicts like this, it could be mat with 0.3, floor with 0.6 probabilities. But the training data set, because we manually masked it, we know what the actual training data set includes. So this training data set is called the ground truth. So when we say ground truth, it is the actual expected output that we are expecting from the LLM, which we can use to compare it and tell LLM that, hey, you are wrong. Better correct your prediction. Right? And does that clarify?
Yes, sir.
Awesome. This is a like very high level understanding of what a neural network is. Just for your information, one full calculation from input layer to output layer and prediction of this is called forward propagation. And all this error correction and trying to adjust these weights in order to decrease this probability, increase this probability, that is called backward propagation. And remember, this model has to do this better job of predicting right next words, not just for this single example. It needs to optimize that prediction for all the examples across the dataset. The main takeaway from this understanding is it will try to adjust the weights, but it cannot guarantee for every example it will generate the right output. So because it is trying to optimize across all the examples, not just for one or two. The very nature of it is the output is always going to be a probability. Therefore, they are called generative models. And therefore, given the same input, you cannot expect this to be giving always the same output. Now, heading back to some of the challenges that people pointed out. So there is this daily usage. You have exceeded your daily usage. There is a limited context length. If you keep giving a lot more context length to it, it has to do a lot of work to understand. And obviously, with those billions of parameters like the theta, you need that kind of computational power behind the scene in order to do all of those calculations that we talk about, the weighted sum for input layer, hidden layer, output layer, right? You need a specialized hardware to do all of that. So it is all powered by a lot of GPUs. And GPUs, as of today, they are costly hardware. So therefore, it comes with these limitations that you have exceeded your daily usage, because it need to like be generous for all the users. And the next thing is up-to-date information. As you saw here, right? So it is being trained on this data set. And because it is trained on this data set, it knows, it has adjusted its weights according to these data sets only. So when you ask a new question, it is not going to say, I don't know, because it is a generative model. It will try to predict like the probabilities. If there is no very great probability value, it will start to pick up something lesser and try to generate it as the next word. So therefore, it will generate some information out of it. But if you compare with the real information, it might be not correct. That's why this problem comes, like hallucinations. And this is by its nature, it will always hallucinate. So because it is a generative at the heart. Yeah, basically, the limitations of it is you have a static knowledge, it has hallucinations, and it has a limited context window. You cannot ask a lot of things in single go. So therefore, in ChatGPT, you ask a question, the answer might not be that good. Then you kind of adopt this approach of prompt chaining, where you again ask a next question by looking at the response of the LLM. You will say like, okay, you are focusing on this more. I don't want you to focus on that. Can you focus on this and try to generate a new output for me, right? So this kind of continuous prompting in a dialogue fashion is called prompt chaining. So of course, in order to do that, LLMs don't carry their own memory or anything of that sort. So if you want to pass all that information, then you need to make all of that information part of your input. These are some of the limitations for an LLM. In order to address these limitations, there is something called LLM agents. Agents are nothing but specialized applications which are built on top of LLM. Basically, these agents will have a memory, and they can have some tools access to them, and they can take some actions and iterate over it. So you don't need to understand this completely, but we'll be looking at a specific example of this. All real world tasks we want the LLM to execute are not just a single dialogue conversations, right? They require some technique called prompt chaining, and there are different techniques of prompt chaining that we can do. So one thing is called chain of thoughts, where we will tell, take a deep breath, think step by step before answering me. Yeah, it sounds funny, but that's one of the techniques that works very well with LLMs. There are other techniques like React. React stands for reasoning and actions, which we will be looking at shortly. But you understand why agents are required, right? Anybody who has not known this terminology called prompt engineering? If everybody has known, you can just admit, say, yes, I know it.
Yeah, we heard it.
Awesome. Thank you, Srini. Like this prompt training is part of prompt engineering. One such prompt engineering technique, which I myself use a lot, is this React. So let's look at what that prompt look like. This is what we send to the LLM. Again, this goes in the input context window. If you see here, the input, the actual input that user has asked is only this. But we are adding all of this additional stuff here before sending it to the LLM. So what we are saying here, I'm just reading it aloud. We are saying, answer the following questions as best as you can. You have access to the following tools. And this tools is a template which we'll be substituting with the actual tools. So when we look at one real world example, you will understand what that will be filled with. And then we are saying, use this following format. So question is the input question that you must answer. Thought is you should always think about what to do. Action is the action to take, should be one of the tool names. You can imagine there is a tool named calculator. So we are telling use only calculator. Like that's what this statement is telling. The action to take must be one of these tools. And the action input is nothing but the input to that action. So if you select calculator as your action, then whatever the information that you need to send to calculator, that is your action input. Then whatever the result that you get from the tool, once you pass that input to the tool and call the tool will give you some output. That result of that action, you record that as an observation. Now you repeat this thought, action input, observation any number of times. Then finally you tell me a thought saying, I now know the final answer, and you give me the final answer. Then we are saying, okay, let's begin. The question is whatever user has asked, and we are giving this agent scratchpad in order to store all of this information. This is one of the prompt technique that predominantly used by a lot of LLM applications. So Shiva, if you want to build that website powered by LLM, this will be one of the default choice in implementing that LLM application. We don't have to sit and write all of these kind of prompts by ourselves. That's where the open source community we can leverage. And one of the awesome frameworks that is available there for LLM applications development is this LangChain. There are a lot of people who contribute to this LangChain framework, and this React is a paper coming from research, and there are already readily available template to give these prompts without us sitting and writing all of this by ourselves. Yeah, so if you are thinking of developing an LLM powered application, I would say start with this LangChain. But I'm not saying this is the thing that you should be using in your production also. But in order to get started, this is the framework to use. So let's look at using LangChain, how this implementation look like. Okay, we are importing a bunch of stuff here. We are loading the necessary tools, and we are loading the agent. By now, you would have just understood the definition of what an agent means, right? And in this case, we are using this LLM model, this GPT-4. We are using this tool named GraphQL tool. It is nothing but a GraphQL client, which will just call this API with GraphQL queries. Here is the important thing. We are mentioning what that agent is. This zero-shot React description. So zero-shot is nothing but, you understood what few-shot means, right? Few-shot is nothing but you pass some examples in your input context. Zero-shot means you are not passing any examples. That's zero-shot, right? So by just using this single line, we are allowing it to actually use this prompting behind the scene when it makes an LLM call. This piece here is just creating the agent, and because I'm using this agent to answer my queries using a GraphQL API, because all my data is there in the database, which is having one GraphQL API layer on top of my database, and I want to get answers in a plain English language. I ask the questions in a plain English language, and I expect the answers in a plain English language, and I expect this agent to do all the heavy lifting of translating in my query into the respective GraphQL query by utilizing this tool here, right? And get me an answer. This is initialization. And this is the piece for actual execution. So this is the query, like I'm asking what species appear in the Empire Strikes Back. And if you see at the application level, for this query, I'm also attaching some knowledge to it. So that knowledge is this. I'm telling, here is the GraphQL schema that is powering my database. So if this is sounding too overwhelmed at this point, that's completely normal. We'll be looking at the trace of it, from which you will understand what is happening behind the scene. So at this point in time, just understand that there is an agent we are creating powered by this GraphQL tool. And the question that we are asking is, what species appear in the Empire Strikes Back? With that, let me actually show you this in action. So basically, the question that is asked is this. As you saw in the code, I'm also attaching this GraphQL schema to it. So primarily for a LLM, it went with this entire input. And if you see, the final answer that it gave me is the species that appear in the Empire Strikes Back Star Wars episode are human, droid, Wookiee. I don't know if all of you are familiar with Star Wars, but that's a exceptionally good science fiction back in the history. Yeah, as you can see, like it came up with the right answer. It used this zero-shot prompting for it. So if you see here, the actual, this is the same prompt, right? Answer the following question as best as you can, and you have the following tools. And here is the actual tool substitution. So basically, we are saying we are substituting with that tool template by actual definition of the tool. We are saying this is the tool name, and the input to this tool is a correctly formatted GraphQL query. And the output that this tool will generate is the actual API response. And the API could generate something like bad request, unauthorized, and all of that. And we also giving single shot, like example input could be like this. And we are saying all that format. You do question, thought, action, action, input, observation, do this a lot many times as you want. Finally, you tell me the answer. Because we are asking it to think in this fashion, what happens is the question goes in, and if you see initially the scratch pad for the thought is empty. Now for this input, the LLM thought, okay, I need to query this Star Wars API using GraphQL to get all the films and their associated species. Probably because I have the access to this GraphQL tool, which takes GraphQL query as input, let me generate a query for it. It says the action I'm going to take is calling this tool, and the input that I'm going to pass to that tool is get all the films. For films, get the title, and for every film, get the species that are connected with this film, and for each species, get me the name. That's the translation, like English translation for this GraphQL query. That's what it generates because the tool requires GraphQL query. And the next step, it actually makes a call to the tool. This is the tool call where the input is the GraphQL query, and the output you see, it generates all that required requested information, which kind of is there in this kind of format. Then the next chain, if you remember earlier, the scratchpad was empty. And because we instructed it to record all your observations in this scratchpad, along with our input, it now recorded the observations. So basically, the LLM thought this and generated this action item. And then when it called this query, the output that it got from tool, it recorded as an observation, like whatever the output that tool gave it to it. And with that observation, then it again said, okay, what is your next thought? And all this work is being done by the agent. The agent is formulating all of this, and then it is prompting LLM to tell what, given all of this information, tell me what is your next thought. Then the LLM started thinking like, I now have the list of species that appear in this episode. And then because we asked it to generate, whenever it has got a final answer, because we asked it to generate in this format, like final answer, it generated like final answer and this. So because this is a React specific agent, when it sees a output like final answer from LLM, it knows that that's the place it needs to stop. So it stops there, and finally it will actually generate the answer, and the answer is given as the final output to the users. As you can imagine, like developing that LLM based applications are just few lines of code with frameworks like LangChain with us. But understanding if things goes wrong, like we should not be blaming LLM because hallucinations are part of its blood. Right, because it is a generative model. So when we see hallucination, there are techniques like RAG where we pass few more information to its input, which will kind of try to reduce the hallucinations. So we'll say, okay, I know that you have outdated knowledge, but here is the up-to-date knowledge. Utilize this, then answer your next-word predictions. And because we have a limited context window length, we need to optimize what we pass to the LLM. So that's where there are techniques like vector search and a few other things. So if you guys are interested, we can probably do more detailed sessions for people who are serious about developing LLM applications. But I think this should give you enough knowledge to understand what LLM is, and in order to get your hands dirty to start playing around with code, to writing some code about on top of LLM. Hope this video was helpful. Thanks for watching.